So here in this problem, we need to obtain the fifth root of a complex number given by square root of 3 plus iota. So let's begin. First, we will consider our complex number z, which is given by square root of 3 plus iota. We want to express this complex number in the form r of cosine theta plus iota times sine theta, that means in the polar form. For this, we need to obtain the value of r and theta. To find out r, all we have to do is take the square root, and within the square root, we'll square the real part and add it to the square of the imaginary part. So this is going to give us a value 2. And to find out the argument theta, all we have to do is take the inverse tangent of the imaginary part, which is 1, divided by the real part, which is square root of 3. Now we know that tangent inverse, here 1 over square root of 3, so that's actually tangent of pi over 6. So that means tangent inverse of pi over 6 is simply pi over 6. So this is going to be the argument of the complex number, and hence we can rewrite our complex number as z equals to 2 multiplied to cosine of pi over 6 plus iota times sine of pi over 6. Right. So now the next task that we want to do here is, we know that our cosine and sine, these are all periodic functions, meaning cosine theta can be also expressed as cosine of 2 pi m plus theta, and sine function, which is also periodic in nature, can be also represented as 2 cosine of 2 pi m plus theta. Your m is an integer which can take the value 0, 1, 2 and so on. Now we can use this particular idea here to rewrite our given complex number as 2 multiplied to cosine of 2 pi m plus theta. So theta in your case is pi over 6 plus iota times sine of 2 pi m plus pi over 6. And this will be complex number z. Now we want to find out the nth root of a complex number. So z raised to the power of 1 over n. So this is going to be equals to 2 raised to the power of 1 over n multiplied to cosine of 2 pi m plus pi over 6 plus iota times sine 2 pi m plus pi over 6. So this entire expression will be raised to the power of 1 over n. Now we will be using the De Moivre's theorem. De Moivre's theorem states that whenever we have cosine of theta plus iota times sine theta, all raised to the power of n. So this is simply equals to cosine of n theta plus iota times sine n theta. Now in the case, our n is actually represented by 1 over n. So we'll multiply the argument of this cosine and sine function with 1 over n. So let's do that. So we have z raised to the power of 1 over n equals to 2 raised to the power of 1 over n multiplied to cosine of 1 over n multiplied to 2 pi m plus pi over 6 plus iota times sine 1 over n multiplied to 2 pi m plus pi over 6. Right. So this is going to be the nth root of a complex number z. Now in that case, since we have to find out the fifth root of the complex number, so we will consider n value to be equals to 5, such that our complex number z will become z raised to the power of 1 over 5 equals to 2 raised to the power of 1 over 5 multiplied to cosine of, so here we have 1 over 5 multiplied to, so we can also take out pi as the common factor. We have pi over 5 multiplied to 2m plus 1 plus iota times sine pi over n. So n value is 5. This will be multiplied to 2m plus 1. So this is the fifth root of a complex number. Since it's a fifth root, so here we'll also have to specify the values of m. So fifth root means we need 5 distinct roots. So for that, we will be considering 5 values of m. So we'll start with m equals to 0, followed by 1, 2, 3 and 4. So for these 5 values of m are going to give us the 5 distinct roots of the complex number. So this is going to be the general solution for the so here let's replace everything. So our z is actually given by square root of 3 plus iota whole raised to the power of 1 over 5. So this general root will be 2 raised to the power of 1 over 5. Whole thing multiplied to the sine of pi over 5 times 2m plus 1 plus iota times sine pi over 5 multiplied to 2m plus 1, and m will be taking the values, where m will be taking the values 0, 1, 2, 3 and 4. So this is going to be the fifth root of a given complex number.